In this slide, we'll talk about sampling. Basically, samplings convert a continuous time signal, as what we have here in this red line, where the horizontal axis is time, continuous time, and then we want to convert it into a sequence of numbers representing this red line. And we do it via sampling. In the third year course, you will do signals and systems and you will learn sampling in more detail, but basically today we'll just very quickly gloss through what sampling does. Alright, let's say we have a signal x of t is given by 2 cosine 2 pi phi t minus pi over 4 plus 1 cosine, this equation here. T is real. And then what we then do is that we can substitute any values of t from 0 to infinity, and then we'll calculate this 2 cosine and this 1 cosine, and we can plot this red line for all t. Now, as you know, we can never remember all points in the horizontal axis. If we want to save in the hard disk, we need to sample these points and we need to quantize. What does sampling means? Well, for example, I'm going to use a sampling of one sample number per, so 1 over 50. That means in 1 second, I'm going to sample 50 times. So if you zoom in now, you realize that the point between this circle and this circle along the horizontal axis, this is 1/50th of a second. Okay? And therefore in 1 second, I would have 50 samples. So this horizontal bar here represents that what am I going to see from this blue dot, blue dashed line, which is the original signal of the read. So even though I am not remembering all the points, sampling theorem tells me that as long as I can sample fast enough, then I can reconstruct the read line perfectly. Okay, but let's not bother about that. So what we realize is that, hey, we're going to choose capital T to be 1 over 50. And small n, of course, starts from 0 until infinity as integer numbers. So this is an integer number, and therefore now I can plug in different n, and big T is constant. So what basically I'm doing is that I'm taking points at discrete time. Now, so we are basically changing small t into capital NT. So you're going to plug in this equation, which is n over 50 is replaced by t, or t is being replaced by n over 50, where n is now an integer value from 0, 1, 2 until infinity. Right. So now when we go from this figure to this figure, we are saying that this is a sampling in time. Okay, sampling in time by this 1 over 50th of a second for big T. The horizontal axis is still time, because I still remembers how time looked like, because by putting different ends, I know where am I in the horizontal time. But you realize that if I drop time and I just remember the sequence, then basically I'm just remembering it as a sequence of numbers. I have no more concept of time. And this is what happened in this step when I convert a discrete time signal into a discrete sequence of numbers. So if you look at this carefully, then what I did was that I simply dropped time. And by putting the 50 inside, I get 2 pi phi divided by 50. Let's try. 2 pi 5 divided by 50 is equals to pi over 5, which is equals to 0.2 pi. So now I have subsumed 2 pi 5 over 50 into this expression here. And now I have a discrete time sequence, and this is the discrete frequency. So the first line represents this first line, but no more concept of time. The second line, 0.4 pi. So let's work it out. 2 pi 10 becomes 20 pi divided by 50. So this is 0.4 pi. So the second cosine has 0.4 pi as its omega. So the first cosine has 0.2 pi, the second cosine has 0.4 pi, and now we have a discrete time signal, a sampled discrete time signal. This guy is actually representing the original time sequence in this manner. So we now are in a position to send this sequence of numbers into Fourier transform, because as you know, the computer can only take in numbers and numbers that are separated by a fixed amount of time, and in fact we don't even care about concept of time. We just take this sequence of numbers and then we can do analysis with it. So what will discrete time Fourier transform on x of n review? We take this sequence and let's say we take 100 samples of it. So there's 100 samples, and we perform Fourier transform. And remember, we need the magnitude spectrum and we need the phase spectrum. And the horizontal axis is frequency, and the frequency here is omega in radian per sample. And then basically what we hope to see is we want to see high values for when it shows that there is a signal of interest there. And it shows that, hey, at 0.2 pi, because along the horizontal axis is 0.2 pi, there is a magnitude 1. And at 0.4 pi, there is a magnitude 0.5. Oh, that's very, very close to what our original signal is. Remember, our signal was this. And we have a cosine at 0.2 pi and a cosine at 0.4 pi. The amplitude is 2 and 1, but this amplitude is 1.5, and the other one is half. So we are losing some information, and the reason is this. Fourier transform does not decompose into cosine. It decomposes into complex exponential. So you'll see that at 1.6 pi radian and at 1.8, there is also some other magnitudes. So we see that our red line decomposes into 4 complex exponential at this 4 frequency with this 4 magnitude, as well as the corresponding phase here. Now, let's go and keep all these values together. We have an amplitude of 1 at 0.2 pi, and with phase of minus pi over 4. So the first one checks out. The second one is 0.5 amplitude and at 0.4 pi. So this is 0.5 amplitude, 0.4 pi radian, and the phase is pi over 6. Pi over 6 is approximately 0.52. Okay, the second one checks out. And the third one, okay, who's the third guy? The third guy is sitting at 1.6 pi, which is here, with amplitude 0.5. And the phase is minus 0.5, so it's minus pi over 6. So this checks out. But what's all this doing? We realize that 1.6 pi is equivalent to minus 0.4 pi. Okay? Because, well, why do we say that? Okay, let's hold the thought. 1.6 pi is equivalent to 0.4 pi because you can think of it as 1.6 pi is rotating anti-clockwise by 1.6 pi angle. But this is equivalent to 0.4 pi rotating clockwise direction. So one is a positive angle is rotating anti-clockwise. Negative angle is rotating clockwise. So they are reaching the same point over here. So that is why I can convert 1.6 pi to minus 0.4 pi. Now there's a minus here and a minus here. We bring the minus outside. and then now we are adding. So this expression here and this expression on top are the same. Okay, let's do the last one. This is 1 magnitude at 1.8 pi with phase of pi over 4. Pi over 4 is 0.78. Okay, again, I will convert this 1.8 pi into a negative angle. So 2 pi minus 1.8 is minus 0.2 pi. The angle remains the same. I bring the minus sign out. Now the plus becomes the minus. Okay, so what have I just done? I've shown you that if I take these 100 numbers and I perform Fourier transform on this, it reveals the magnitude and the phase spectrum. The magnitude here and the phase here. And I can then, for each of these value that is non-zero, I can write the equation representing what it means as complex exponential with the magnitude, with the frequency, as well as the phase. Now remember that I should add all this up. When I add all this up, you realize that basically I can collect 0.2 pi and this minus 0.2 pi together. So this term and this term can be collected together, and it will give me 2 cosine 0.2 pi n minus pi over 4. And what about the other one? This term 0.5 at 0.4 pi radian with this phase shift for pi over 6, as well as this other guy 0.5 minus 0.4 pi plus pi over 6. I can collect this term as well. And it will reveal that, hey, I have 1 cosine at this frequency phase shift of pi over 6. So the take-home message is this. To deal with Fourier transform using the computer, we normally first take the time representation in continuous time and we sample it. So this is a discrete time, and then we throw away the t, so we have a discrete sequence. We take this discrete sequence, and because we know how to do it and we get this expression, we now want to see whether we can generate this expression using the Fourier representation of the magnitude and phase spectrum. So when we do the decomposition, we get this representation. And here I show you that the non-zero entries are then expressed as each of these equation of complex exponential of different magnitude at the frequency with the phase. We add all of them up, and we show that, hey, we get back the 2 cosine wave at that particular frequency with the correct magnitude and phase, and shows that Fourier transform allow us to represent the original information with no loss. Okay, in the next few slides, I will talk about how it does it. Thank you.